Okay, so this is the continuation of our lecture on open methods. So before we discuss the Newton-Raphson method, and in this lecture we will be discussing another one. We call it the second method. Second method is somewhat similar with the uh, Newton-Raphson. So if we observe Newton-Raphson, we need to find the derivative or f prime x of the function. So sometimes taking the derivative of a function is not that easy to do. So another method to avoid taking the derivative is to use the second method. So if you remember in calculus, our derivation of derivative dy dx, the slope. So if we have a function, so if this is our function f of x. Now, if we want to determine the slope of this function at a certain point, we just need to take the derivative of that function and substitute the value of the x at that point. And when we derive that, we use the second line. So we connected first before we go to the tangent line here. This is our tangent line. We used first the second line. The second line is this one. So this is our slope of the second line, while the green one here is the tangent line. And we said before in calculus, when the slope of the second line, or the other way around, if we name this one point P and this one point Q, and the distance between them and the x-axis, we usually call this one the delta x. So when Q approaches P, that means delta x is also approaching 0, because it becomes very, very small, infinitesimal. Then what happens is the slope of the second line is also approaching the slope of the tangent line. So that's the definition of a tangent slope. And that one we can actually approximate as the derivative of y with respect to x. If you remember, delta y over delta x, if you take the limit of this one when delta x is approaching 0, then you get the slope of the tangent line. But if you don't take delta x approaching 0, then that slope is just the slope of the second line. So here in second method, instead of using the derivative, we can use the second line, the slope of the second line. So instead of f prime x in the equation, we will approximate this one into delta y minus delta x. So this is an approximation, because delta x is not approaching 0, so it has a value. It's not derivative. It will be equal to the slope, which is f of x. If we call this point, we call it x1. This will be f of x1. Then this point at P, x0 and f of x0. So this will be f of x1 minus f of x0. That's the y, delta y, y2 minus y1, all over x2 minus x1. But this one is x1 minus x0. So this is only this is the difference with the Newton-Raphson method, or the Newton method. We use, instead of this one, we used actually this one, delta y over delta x, as delta x approaches 0. But this time we will be using this one. So if we remember our formula in the Newton-Raphson, this one, yeah, xn plus 1, xn minus f of xn divided by x prime xn. So what we will do is we just change that f prime xn into this one. In general, we can make this one f prime x. We can approximate it. Instead of f of x1 minus f of x0, we can make it f of x n minus 1 minus f of xn all over x of n minus 1 minus x n. So this expression, we will be using this one in, we will substitute this one into our Newton-Raphson formula. So what's our Newton-Raphson formula is xn equals, or xn plus 1. xn plus 1 is equal to xn minus f of xn all over f of xn prime. So this is the Newton-Raphson or Newton method. So now, instead of derivative of f, we will insert this one here. So our new formula now will be xn plus 1 equals xn minus f of xn all over that one, f of xn minus 1 minus f of xn all over xn minus 1 minus x. And if we simplify this one, so our final formula now will be for xn plus 1. This will be xn minus, we put the denominator in the numerator, we multiply that one with f of xn. So this will be f of xn multiplied by xn minus 1 minus x. This is xn and all over f of xn minus 1 minus f of xn. So this will be now our new formula for the second method. Instead of taking the derivative, there's the derivative here. This is the advantage of the second method. But the disadvantage of the second method is, of course, it will take much longer than that of the Newton-Raphson method. This is Newton-Raphson method. So let's try to solve our previous example, and let's compare them again and use this one. So before, our example was f of x equals x raised to 3 minus 0.3. And we already know one of the root this function. We solve them using our different methods. It's around 0.6, I think 6694, up to 4 significant figures. Now we will be using second method instead of the Newton-Raphson method. And to do that, solution. So the first step for the second method, the difference with the Newton-Raphson. In Newton-Raphson, we are solving for the slope given 1 point. Remember, given 1 point. But this time, in second method, we are solving for the slope again, but it's not the tangent line, but it's the second line. And the second line, we need 2 points to solve for the slope. So here in second method, we need two initial values for our root, x0 and x1 usually. And it is not necessary that the root is within the interval of the two guesses. We call them initial guesses, because it's not a bracketing method, it's an open method. So it's not necessarily bracket the root. Any value will do. But we know the value that's around 0.6694. So we can choose 0 and 1 or 1 and... so let's try 1 and 2. So 1 and 2 does not bracket the solution. We know the solution is 0.6694. So we can use 1 and 2. Let's try what will happen if we use our initial guesses to be equal to 1 and 2. So here, the first step, x0 will be equal to 1 and x1 will be equal to 2. So next, x0, x1, so the next thing that we will be doing is to solve for x2. x0, x1, x2, xn plus 1. Remember, xn plus 1. So if xn plus 1 is equal to x2, then xn will be equal to x1 and xn minus 1 will be equal to x0. So our formula now for x2 will be equal to xn. So this is xn plus 1. Remember, our n now will be 1. So x1 minus f of x1, f of xn, here, f of xn, then multiply it with the difference, xn minus 1 and xn. So what will be our xn minus 1? Our xn minus 1 will be x0, because our n is 1. x0 minus x1. Then we divide this with f of xn minus 1 minus f of xn. So what is our f of xn minus 1? That's x0, so this will be f of x0 minus f of x1. So that's the formula for x2. So if we continue to solve that, substitute the values. What is x1? x1 is 2 minus what is f of x1? It's just f of 2. So it's 2 cubed minus 0.3. Then we multiply this one with x0, which is 1, minus 2, x1, all over f of x0, which is f of 1, 1 cubed minus 0.3, minus f of x1, f of 2. So if you plug in now this one into your calculator, your answer will be around 0.9. 0.9. So if we try to see our new value now, x2 is 0.9, and we choose 1 and 2 as our initial values, so the next value is not between 1 and 2, so meaning it's not really a bracketing method, it's an open method. It goes down outside the interval of the two initial guesses. So after that, we can now proceed again to our next value, x3, x2, x3, x1 plus 1. So our new xn now will be the last xn plus 1, which is x2. So instead of x1 now, this will be x2 minus f of x2 times our x0 becomes x1. That is n minus 1 because our n now is 2. So here n equals 1. Here n equals 2. So x1, then n minus 1 is x1. Oh, wait. So this is x1 minus f of xn. Our xn is x2. So this is x2 all over f of x1 minus f of x2. So there's a pattern here. You just look at the pattern. Then it can be solved easily. So this will be x2 is 0.9, so 0.9 minus f of 0.9 minus x1 is 2, so 2 minus x2, 0.9, all over f of 2. This is now f of 2 because our previous xn minus 1 is x1, which is equal to 2. So minus f of x2, where x2 is equal to 0.9. Then calculate this again. What is f of 0.9? 0.9 cube minus 0.3, f2, 2 cube minus 0.3, and so on. So the answer will be, if we round this up to 0.835, 835 835 098 835 098, and still far away with our true value, which is 0.6694. So we continue our iteration. So next now, x3 after x3, we have now n equals 3. So this will be x3 plus 1, so x4. Then xn, x3 minus f of x3, x2 minus x3, n minus 1 minus xn, all over f of xn minus 1, x2 minus f of x3. So it will be equal to, this time our x3 is 0.835098. So minus f of x3. So that will be f of what is x3, that is 0.835098. You substitute this one, you cube it, then minus 0.3. Then you multiply it with x2 minus x3. What is x2? x2 is 0.9. Then you subtract 0.835098. Then all over f of 0.9 minus f of 0.835098. Then calculate this again. So the answer will be 0.7 10091 10091. So that is our new value. So let's continue. It's still far away from our true value. So this time now it's n equals 4. N equals 4. So we will be solving x of 5, 4 plus 1. So this will be x4 minus f of x4 times x3 minus x4 all over f of x3 minus f of x4. So this will be equal to, our x4 is 0.710091 minus f of x4, f of 0.710091, multiply it with x3 minus x4. x3 is 0.835098 minus 0.710091, and you divide this with f of 0.835098 minus f of 0.710091. Calculate this again. Then your answer will be 0.6 0.6777 4, 5. 4, 5. It's 0.76777. 7745. And it's still not our true value. It's not still 0.6694. So we still continue our iteration. So next will be x6. x6. x5 minus f of x5 times x4 minus x5 all over f of x4 minus f of x5. So this will be our x5 is 0.6777745 minus f of that times x4. x4 is 0.710091 minus 0.6777745. Then all over f of 0.710091 minus f of 0.6777745. Then calculate this again. Our x6 now will be equal to 0.66991. 0.66991. So our value now will is closer now to the true value. The true value is 0.6694, and we are doing it x6. Our this is our fifth iteration now already. So maybe the next iteration we will get the closer value to the true value, x7. So for x7, let's do this again. I think this will be the last one. x7 will be equal to, let's try to direct the solution. x7 is equal to x6. x6 is 0.669914 minus f of x6. f of 0.669914. Then x4 or x5 is 0.6777745 minus 0.669914. Then all over f of 0.6777745 minus f of 0.66914. Then calculate this again. x7 now will be equal to 0.6694388. So we can now stop the iteration. We already got the up to 4 or 5 significant figure, 0.6694. So this will be our final answer. So that is second method. So the only advantage of second method compared to the Newton-Raphson is the fact that it doesn't use the derivative. So if you don't know how to take the derivative, or you cannot implement a derivative into your program later on, we will implement this one in laboratory. So it's easier to write a program for a second method, although it's a longer solution compared to that of the Newton-Raphson. So this is second method. Next lecture, we will go to the next topic, and the next topic will be about roots of polynomial. Okay.